Okay, it's time to start talking about how magnetic fields affect things, how they exert forces on things like charges. So that's the first of our explorations. We'll do some others. All right, let's see how a magnet deflects a stream of electrons.
In this demonstration, I have a tube connected to this power supply. When I turn on the power supply, we get a nice beam of electrons flowing from here to here. Now I also have a magnet, South Pole, North Pole, and what I'm going to do is I'm going to bring the South Pole up towards this end of the tube. Now the question is, which way will the beam deflect? Will the beam deflect up? Will the beam deflect down? Will it deflect towards me? Will it deflect away from me? Or will it not deflect in any way?
So we see that it deflects upward when he brings the South Pole in.
So bringing the South Pole in this way caused the beam to deflect up.
What do we learn? Magnetic fields exert forces on charges, but they do it in sort of a weird way. There is no magnetic force on a particle at rest. There's also no magnetic force on a particle moving parallel to the magnetic field. And that's something which is not illustrated here but is also true. There's no magnetic force on a neutral particle no matter how it's moving. So magnetic forces affect charges, but not if they're aligned and not if they're at rest. On the other hand, if they're not aligned, if there's some angle between the two, then it turns out there is a force on the particle, and it's perpendicular to the velocity, and it's also perpendicular to the magnetic field. So if we think of this as a plane that contains the velocity and magnetic field, and there will always be a plane that contains them, then the force will be perpendicular to that plane. It will be largest when they're at right angles to each other. It's 0 when they're completely aligned, and then it grows, and then it gets largest when they're perpendicular, and then not shown here, but it would decrease as we kept increasing the angle. This is sort of a strange thing. In vector algebra, we capture this with something called the cross product, and we say that the force vector is the charge times the velocity vector crossed into the magnetic field. And in vector algebra class, they'll do a lot about defining the cross product and how do you figure it out in terms of the component vectors and so on. We won't do a lot with this vector notation, but we can think of it as a shorthand for the force being perpendicular to both v and b, because cross products are always perpendicular to the two things plugged into the cross product. And I at least will probably say, remember the force is qv cross b, which again, you're not expected to compute algebraically what v cross b is, but it reminds you that it's a cross of the two, so it's always perpendicular. The magnitude turns out to be the magnitude of the charge times the speed times the magnitude of the field times sine of the angle between them. Again, 0 when they're aligned and maximized when they're 90. The direction is again given by a right-hand rule. Your textbook says put your thumb along the velocity, your index finger along the magnetic field, and your middle finger will point along F. When I learned it as, and we'll probably continue to refer to it this way because it's how I learned it, as the index finger along V, the middle finger along B, and your thumb will point along F. But either order is fine. This is what's called a cyclic permutation, and as long as you keep them in the same order of fingers and vectors, it doesn't matter if you rotate them through a little bit. Use whichever one you find most convenient. And we illustrate that here using their thumb. V crossed into B goes to F. Even if it turns out, and I guess this is why they do it, that there's an angle between your thumb and your finger. Keep in mind that this right-hand rule assumes the charge is positive, because this is really giving you V cross B, but the force is QV cross B. So if Q is positive, we're fine. But if Q is negative, then F would be the negative of V cross B, which would point the other way. It would point downward. So for negative charges, you have to flip the direction of F. Also, apparently, if you think about it, you could probably also use a left-hand rule, but I think you open yourself up for a lot of trouble if you start invoking left-hand rules. So it's probably better to just take the right-hand rule and remember to flip it for negative charges, because as always, negative charges are annoying. All right, so give this a go. If an electron moves through a magnetic field as shown, in what direction is the electron accelerated? Well, here we have, if we just draw our vectors a little bit, we have V and B. So they're at right angles, which is good. And if I curl my fingers, I would have to curl them this way, my fingers that way. I would get that my thumb pointed out of the board like that. But that's actually not quite right because it's an electron. So it has the opposite sign. So it goes into the page. All right, a proton moves rightward above a long current wire carrying current also to the right. What direction is the magnetic force on this proton? So we remember that for a current moving this way, we put our thumb along that direction and our fingers curl in the direction of the field, which would be like this. So we see that the field is coming out at that point. Well, really at this point, but at all the points along here, the field is out of the page. So now I take my finger of V along that, and I take my, so V along this way. I'm going to kind of sketch it, but B out of the page, and we find that the magnetic force would be downward. Drawn a little bit more nicely by the people who made the textbook, we get here's our magnetic field and here's our force. This will actually be really important in the next thing we do when we talk about fields, forces of fields on currents. All right, now consider a charged particle, let's say a positive to make life easy, moving perpendicular to a uniform magnetic field. So there's a field in this case as drawn going into the board, hitting into the page, and we have a positive charge which is moving this way, but then it would feel a force which is sort of towards the southwest, and it would curve. And as it curved, that force would swing as well. So at this point, moving over towards the due west, it would feel due south, etc. As moving due south, it would feel a force due east. The force on the particle is always perpendicular to the motion. But having a force which is always perpendicular to your motion is the recipe for uniform circular motion. So this particle is going to go around in a circle as long as it's in that uniform magnetic field. An important note that this is the case when the field is uniform. If the field were varying, then the force might not be directed towards the same point all the time, or it might not be the same strength all the time. So this is a very common test problem type thing, but keep in mind that it's a very restricted case. It's not quite as bad as assuming things are frictionless, but it's the same sort of thing where if you lose track of the fact that problems are usually this way but don't have to be this way, then they can trip you up on the exam. All right. The magnetic force must provide the centripetal acceleration, of course. So the magnetic force is the net force, which is got to be the centripetal force. So QVB has to be mv squared over r. So the radius of this thing has to be mv over qb. As a really interesting kind of strange aside, hey, that's the momentum. And that will end up being important in relativistic magnetics, which we will not be doing, but comes back to saying we can extend this into a relativistic and quantum mechanical system by replacing mv with its better defined thing called p. All right, how about a particle whose velocity is not perpendicular to the uniform B field? So in the case we had here, a particle which was going a little bit into the page as well as along the page. What would happen to the path that it takes? Well, the component parallel to the field exerts, it feels no force, right? The component is unchanged because there's no force for motion along the lines. And the perpendicular component will swing the velocity around in a circle. So we get what's called a helix. And we say the particle undergoes helical motion. This idea where it kind of spirals around the magnetic field lines. It can still move forward, but only in this kind of looping motion. For us, one of the interesting applications is we can map the magnetic field of the sun because the plasma that makes up the sun, which is a charged gas, gets trapped and spirals along the field lines. So what we're seeing here is actual gas that is trying to escape the sun and gets looped back along the field lines. So even though it looks like an illustration from a textbook, it is an actual picture of the sun, and we're actually seeing these particles as they get trapped on these field loops, especially sort of here in the corona, which is kind of interesting, like that one, where you're actually seeing magnetic field exit the sun and enter the sun. You'll also notice that where things re-enter the sun, you're seeing brighter things, and that actually in astrophysics ends up being really important. There's a lot of energy that's going on as stuff re-enters and exits the sun at where those field lines are starting to get close together. Right. An important technological device is something called the cyclotron. It was originally invented to study fundamental particle physics, to speed stuff up really fast so we could smash them together and see what comes out. That's been sort of superseded. That's not the most common way to do fundamental physics, but it now is also used to generate the radioactive isotopes that you need to do certain types of medical imaging, like PET scans, where you need some radioactive material, and it's very short-lived, so you can't build it at a factory and just ship it to the hospital. Instead, the hospital has to have its own nuclear cyclotron running, or at least some place very close by. And the parts of a cyclotron are something that does high voltage oscillating potential, so something goes, sometimes this is positive, sometimes this is negative, going back and forth, but with very large, very, very large potential. We put some source of protons in the middle, doesn't really matter what they are, and then they enter this magnet, and the magnet is in two parts, each called a D, and the magnetic field is roughly uniform and pointing, say, in this case, upward, and so the positive charge spirals around a half circle, and then it accelerates across that gap, and then spirals around again and accelerates. So each time it's going faster as it enters the D, so it tracks out a bigger and bigger circle, and eventually it exits here in a highly collimated beam of very, very high speed. The large potential is designed to flip while the protons are stuck inside the D. The Ds are called Ds because, in fact, they look like the letter D, which I think is kind of funny. Since they accelerate every time they go across the gap, in other words, they're accelerated this way, and then by the time they get back on the other half of the circle, we flip the potential, so they're accelerated again. And so they spiral outward, and they exit here with very high energy. All right, circle in blue the cases where the particle is positive, and circle in red the cases where the particle is negative. So let's take case A. If I put my finger along V and my index finger into the page, I find a force that is going outward. Or I find V cross B. This is V cross B, and it's pointing the wrong way. And we know that F is Q times that. So since I need to have F pointing in, I need that for F, otherwise it won't go in a circle, then Q must have been negative so as to flip the sense of V cross B. I could do the same rigmarole for B, or I could just say all I've done is flip the sense of V. V is now pointing this way instead of this way, so I'm introducing a minus sign here, which is going to flip the force, unless I also introduce some other minus sign, so I've got to flip the charge as well. So this one has to be positive. If I look over at case C, I put my index finger that way and my middle finger coming out, and here I see again that the force is outward. Sorry, that V cross B is outward, but I need the force to be inward, so this has to be a negative particle, and that tells us this has to be a positive particle.